I'd like to do a quick video on spring mass energy. We've been talking about spring mass systems in class, and here we've drawn one. We've got a spring right here. We've got a little mass. And we assume this is sliding back and forth on a frictionless surface. And if we pull it to this spot here, positive A, and we let it go, then what's going to happen is it's going to begin to oscillate. It's going to do something like this in time. So that's what the system's going to do. And what we want to do is consider the different types of energy that it can have. There's different types of energy based on what we've talked about previously in class. One is the spring potential energy that's given by 1/2 kx squared. And the other is the kinetic energy. It's given by 1/2 mv squared. So as it's oscillating back and forth like this, it's got these different types of energies going on. So the total energy is just given by the sum of the two. 1/2 kx squared, the spring potential energy or the elastic potential energy, and the kinetic energy, 1/2 mv squared. Now, one of the questions I'd like to consider really quickly here is, are both of these energies exactly the same at all times, or do they vary with time? Well, they vary with time. As you might understand, the spring potential energy will be greatest when x is greatest, okay? Now that means if this is the zero position right here, where the system is at rest, then stretching it out to positive A, where that's your amplitude there, that'll be the largest possible value of x that we can put in there. So if I put in A for x squared, or A squared for x squared, then I'm going to get the maximum energy that the system can have. Likewise, if I compress the spring by taking the mass and moving it over to here to minus A, that also will be a deviation from the 0 point. And that compression of the spring will also give elastic potential energy equal to 1/2 Ka squared in that case. So when the spring is basically at its greatest extent, either positive A or minus A, the mass is just at a turning point. It's going out and then it's coming back. So it's not really moving with any velocity right at the moment it reaches maximum amplitude. So it goes all the way out there and then it reaches maximum amplitude and stops and then it reverses direction. Same thing here. It goes out, stops, and reverses direction. So the kinetic energy is going to be 0 at these points of maximum excursion. And that's where the potential energy is greatest. So let's take a look at that. We see here, I've colored it. So the spring potential energy is going to be max right here, where A is your amplitude, like that, in those spots. And at those spots, your kinetic energy will be 0. So your spring potential energy will be greatest here, here, and here, but your kinetic energy will actually be 0 there because there's no velocity. So where will kinetic energy be greatest? Kinetic energy will be greatest when the stretch on the spring is 0. So if I have a 0 displacement of x, and I'm right on this axis, then what that means is that I have no potential energy. So my total energy has got to be composed of the kinetic energy at that spot. And again, I said we're assuming a system has no friction. So what we're going to have is a constant amount of total energy that will just vary between potential energy and kinetic energy. So these spots where it crosses the axis, that's where you're going to have maximum kinetic energy. So it goes back and forth between these guys. Now here's a question. See if we can apply our knowledge. What will the velocity of the system be when its x position is A over 2? So in other words, it's halfway between its maximum amplitude and 0. So this value here would be A over 2, something like that. You can set up the equation like this and say the total energy is 1/2 kx squared plus 1/2 mv squared. And what you can do is you can plug in that value for x, A over 2. So if we plug it in here like that, we've got it. And now we've got 1/2 mv squared over here. But what do I do for the total energy? Well, I can remember that at its extreme, when this spring is stretched maximally out here to positive A or there to minus A, that value of the total energy is 1/2 Ka squared because there's no kinetic energy there. So way down here, what I can do is I can basically substitute in for total energy. I can sub in 1/2 Ka squared. So that's nice because now I've got an A term here and I've got an A term over here. That'll allow me to simplify things further and then hopefully solve for V. So we do that. I notice that there's a 1/2 everywhere, so we cancel the 1/2 everywhere. And then I subtract A over 2 quantity squared. I subtract that from both sides and I get on the left-hand side K times A squared minus A squared over 4 because that's just a over 2 quantity squared, and then that leaves mv squared. Remember, we got rid of the 1/2. If I work this down a little bit more, I get, this is 4a squared over 4 minus 1a squared over 4. It's going to leave me with 3a squared over 4. And now I can take the square root, and I basically get something like this. A over 2 times the square root of 3k over m. That would be the velocity at the point where it was 1/2 of its maximum amplitude away from 0. So hopefully I've shown you here that there is this variation of kinetic and potential energy in the spring mass system as it oscillates back and forth, and I've shown you an example of how you could solve for the velocity at a given amplitude.